So, for we have discussed various discrete distributions, and many of them we gave direct origins, that what kind of experiments lead to those distributions. Apart from that, there are certain distributions such as the distributions which can be represented as a power series, because you observed say geometric distribution where you are getting a term q to the power j minus 1 into p, where j is from 1 to infinity. So, this is something like a power series in negative binomial distribution also, and then you have a finite polynomial sums like in binomial distribution, or in Poisson distribution you have certain term e to the power and then you have power series. So, there is a general family of power series distributions that we will talk little later. Firstly, let us discuss some spatial continuous distributions. As in the case of discrete distributions, the simplest example of a continuous distribution could be where the density is uniform or density is a constant. For example, you consider a rod with a uniform weight. For example, you consider this sheet, and here the sheet it is the thickness or say weight of this sheet at every point will be same. So, if we consider say this portion of the pen, then here in this portion the density, the weight, the thickness or the width is constant. So, if the density is a constant over a certain interval, say a to b and 0 elsewhere, we call it uniform distribution. Now, what should be the value of the constant? That can be determined by the condition that the density must be non-negative and the integral of the density must give you 1. So, k must be non-negative and integral of k from a to b must be 1. This means k into b minus a is equal to 1. That means, k is equal to 1 by b minus a. So, a continuous uniform distribution has the probability density function given by 1 by b minus a is less than x less than b, 0 for x lying outside this. We will use the notation E w for writing elsewhere. Of course, here it is immaterial whether we use strict inequalities or we may use equalities at some points less than or equal to, because the probability of a point is 0. So, in a continuous distribution, inclusion or exclusion of a point does not make any difference. So, if you look at the shape of this distribution, suppose a and b is here, then 1 by b minus a is this. So, it is a, you can say, a plateau kind of thing, the continuous uniform distribution. We may look at some of the properties here. So, what is the first moment? That is expectation of x. So, it is equal to integral x divided by b minus a dx from a to b. So, that is half b minus a x square from a to b. So, that gives us b square minus a square divided by twice b minus a, that is equal to b plus a by 2. You can easily see that it is the midpoint of the distribution, which is understandable because the density is constant and therefore, the average value must be the midpoint. Now, since it is a finite interval, we can look at the moment of any order here. The moment of any order will exist x to the power k divided by b minus a dx. So, this is equal to b to the power k plus 1 minus a to the power k plus 1 divided by k plus 1 into b minus a. If you have b is equal to a, then it will not be a continuous distribution. So, in particular mu 2 is equal to expectation of mu 2 prime, that is expectation of x square, that will be equal to b cube minus a cube divided by 3 into b minus a, that is a square plus a b plus b square divided by 3 into divided by 3. So, the variance of the uniform distribution, that is mu 2 prime minus mu 1 prime square, that is a square plus a b plus b square by 3 minus a plus b whole square by 4. So, after some simplification, a plus b by 2 whole square. So, we can make simplification here. This turns out to be b minus a whole square by 12, that is sigma square. So, the standard deviation of this distribution is b minus a divided by root 12, that is 2 root 3. So, you can see here the range of the distribution is b minus a, and the variability is b minus a divided by 2 root 3, which is slightly, you can say, much less, because 2 into root 3 is 1.71. So, this becomes b minus a divided by 3.42 kind of thing. So, this is much smaller than the range, and it is because of the uniformity that the variability is much smaller. However, if b and a are far apart, that means, if b minus a is a large number, then even though after division the variability will be high. So, for example, you have too much of flatness, say a to b, and the value of this is like this 1 by b minus a. So, basically it will become much smaller here if you plot 1 by b minus a here. So, that shows that the variability increases if the range of the distribution increases. One may also look at mu 3 and mu 4 and calculate the measures of skewness and kurtosis. Obviously, it is a symmetric distribution, therefore, measure of skewness will be 0. However, measure of kurtosis will depend upon the difference between a and b, as you have seen here. If the difference between a and b is smaller, then the density will be plotted at a higher this one. If the difference between a and b is large, then it will be quite flat. So, mu 4 will be dependent upon the value of b and a. We also look at the plotting of the cumulative distribution function, that is integral minus infinity to x f x t dt. Since the distribution is 0 up to a and beyond b, that means, this is going to be 0 for x less than a, and it is going to be 1 for x greater than b. You may put equality here also, it does not make any difference. However, if I am considering x to be between a and b, then it is integral from a to x of 1 by b minus a dt, and this value is equal to x minus a by b minus a. Therefore, the CDF can be written as 0 for x less than or equal to a, x minus a by b minus a for a less than x less than b, and 1 for x greater than or equal to b. You can easily observe that the function is absolutely continuous, the derivative will give you the density, and the endpoints a and b of the intervals, the function is continuous. If we plot this, suppose a is here and b is here. So, up to a it is 0, from a to b. So, suppose this is the value 1 here. So, it is a line here and thereafter it becomes 1. So, it is a straight line joining the point 0 to 1 here. We may also look at the moment generating function. E to the power t x dx divided by b minus a from a to b. So, it becomes e to the power t b minus e to the power t a divided by t b minus a. Obviously, at t is equal to 0 this is not defined, but at t is equal to 0 this is 1. So, this is t not equal to 0 and t equal to 0. Let us consider a Poisson process. Consider a Poisson process with rate lambda. Of course, lambda is greater than 0. Let us denote by say t be the time of the first occurrence. So, we know that it is a Poisson process, the number of occurrences will follow a Poisson distribution. So, at some point of time we start observing the process. For example, we go and stand at a ticket counter of certain cinema, and then we want to see when the first customer arrives. We are, suppose I am a traffic police person and I go to the my designated traffic crossing. Now, when I am standing there, I start observing when is the first accident taking place. So, if we consider t as the time of the first occurrence from the time when we start observing, then t is a continuous random variable, because it is the time. So, we want the probability distribution of t. What is the distribution of t? So, we can look at a event, say probability t greater than say small t. What does it mean? That means, if we are observing the process from certain time t, then up to the time small t, if we are starting from 0 up to time small t, that event has not taken place. That means, in the interval 0 to t, the number of occurrences is 0. So, if we are considering this Poisson process as x t, then the event capital T greater than small t is equivalent to probability that x t is equal to 0. Because if there is no occurrence in the interval 0 to t, then capital T is definitely going to be greater than small t and vice versa. So, these two events are same. However, the distribution of x t is assumed as a Poisson distribution, because we have made the assumption here that it is a Poisson process with rate lambda. That means, probability x t is equal to n is e to the power minus lambda t lambda to the power n by n factorial. So, here if I put n is equal to 0, then this is giving me e to the power minus lambda t. So, of course, this statement is true if t is greater than 0, because we are observing from certain time onwards. So, this is for t greater than 0, this probability will be 1 if t is less than or equal to 0. So, if we consider the cumulative distribution function of t, that is capital F of t, it is 1 minus probability of t greater than t. So, from this derivation it is equal to 0 for t less than or equal to 0, and it is 1 minus e to the power minus lambda t for t greater than 0. So, now you can observe here we are able to derive the CDF of this continuous distribution, and it is an absolutely continuous function. So, if we differentiate this, we can get the density function of the time for the first occurrence during a Poisson process. So, the probability density function of t is f t equal to lambda e to the power minus lambda t for t greater than 0, and it is equal to 0 for t less than or equal to 0. This is known as negative exponential distribution. So, this is a continuous distribution, and this distribution arises as the distribution of the waiting time in a Poisson process for the first occurrence of the event, whatever occurrence we are trying to observe. Naturally, we would like to look at the properties of this distribution. So, for example, the shape of the distribution at t equal to 0, it is 0 up to 0, and at t is equal to 0, the value is equal to lambda, and then e to the power minus lambda t, because lambda is positive. So, this will be less than 1, and this will be a decreasing function, because and you will have it decreasing to 0 as t tends to infinity. Let us look at its moments, etcetera. So, if we consider a general moment of the kth order, it is expectation of t to the power k, that is equal to t to the power k lambda e to the power minus lambda t dt 0 to infinity. Now, this is nothing but a gamma function. So, this becomes lambda gamma k plus 1 divided by lambda to the power k plus 1. So, this is equal to lambda k factorial divided by lambda to the power k plus 1, that is k factorial divided by lambda to the power k for k equal to 1, 2 and so on. Of course, here you can see that if k was 0, then actually it was nothing but the integral of the density, which would have been 1. So, the moments of all positive order exist here. In particular, we can calculate mean, variance, etcetera. So, for example, mu 1 prime, that is the mean of this distribution, is equal to, if I put k equal to 1 here, I will get 1 by lambda. So, if the rate of occurrence is lambda per unit of time, then the waiting time, the average waiting time for the first occurrence is 1 by lambda. So, which is very natural to understand. Suppose I say that in 1 hour 2 events will occur. So, roughly average waiting time for first occurrence will be 30 minutes. We may also look at mu 2 prime, that is equal to 2 by lambda square, and therefore, mu 2, that is the variance, will become 2 by lambda square minus 1 by lambda square, that is equal to 1 by lambda square. So, you can observe here the variance of the exponential distribution is square of the mean. We may calculate mu 3 prime, that is equal to 6 by lambda cube, mu 4 prime will become equal to 24 by lambda to the power 4, using the relationship between the non central and central moments, mu 3 is equal to 2 by lambda cube and mu 4 is equal to 9 by lambda to the power 4. From here we can calculate the measures of skewness and kurtosis. So, beta 1 is equal to 2 by lambda cube, that is mu 3 divided by sigma cube. So, this is sigma square. So, this becomes 1 by lambda cube, that is equal to 2, which is always positive. That means, no matter what the value of lambda is, the exponential distribution is always positively skewed. So, this you can see from the shape of the distribution also, because here it is a constant. Similarly, if we look at say beta 2 is equal to 9 by lambda to the power 4, that is mu 4 divided by mu 2 square, that is divided by 1 by lambda to the power 4 minus 3, that is equal to 6. So, no matter what the value of lambda is, it is always having peak higher than the normal peak. So, this is always positively skewed and always peak high, that is higher than the normal peak. Now, here you observe this is slightly different from the earlier distributions. In binomial distribution, in Poisson distribution, in geometric distribution, etc., the condition for the skewness and the kurtosis was dependent upon the parameter. That means, like in the binomial distribution, if p was half, the distribution was symmetric. If p is less than half, it was positively skewed. If p was greater than half, it was negatively skewed. And similarly, if p q was less than 1 by 6, it was leptokurtic. If p q was greater than 1 by 6, it was platykurtic, etc. Unlike those distributions, same thing we observed in the Poisson also. In the Poisson distribution, the measure of skewness was 1 by lambda. So, it was positively skewed, but as lambda becomes large, it approaches the symmetry. Similarly, in the measure of kurtosis was also having lambda in the denominator. But here these measures beta 1 and beta 2 are constant, and they will always have the same behavior, that is positively skewed and the peak higher than the normal peak. In the next lectures, we will be considering extension of this concept of the time, because here the negative exponential distribution is obtained as distribution of time for certain occurrence. So, we will consider extension of these concepts in the next lecture. Thank you.